Hi everyone, in this lecture, in this part of our general chemistry lecture series, we're going to be talking about measurements. In the next lecture, we're going to be using these ideas, so this is probably the most important lecture from this unit because you're going to use it literally in every other unit and to an incredible degree, and you're going to even use it in maybe your physics course and any science course you get into. So maybe for some of you this is a review, but what we're going to be talking about today is measurements, next time dimensional analysis, two very fundamental ideas. So what is a measurement? Well, in chemistry, and this sounds incredibly Neanderthal of me to say, we take a lot of measurements. And in fact, I take so many measurements. In the last lab alone, I think I've measured out in a pipette maybe 100 times. I've measured in a graduated cylinder. I massed on a balance. These things. It's a very common practice in analytical chemistry. But how can we unify it, right? Because if you notice, we have the metric system, we have the imperial system, who's right, who's wrong. Well, in science, we go with the metric system. So I'm going to introduce the metric system to you now. We're going to talk about conventions of that. We'll talk about prefixes. We'll talk about derived units. So how do we measure things in the metric system? Well, it's quite simple. We have ideas that we inherently know: length, mass, time, temperature, light intensity. If you take physics, you might even do current, how much you have, these kind of things. So let's go through each one. So the metric system. You can have an idea expressing how long something is. So from here to here in a one-dimensional move motion, how far am I going? Okay, that's the idea of length. And this basically asks, how long? Okay, so length is asking, sorry, I thought I was getting interrupted here. So for length, they're asking how long. And we quantify this with something that you've probably heard before, the meter. Okay, so how long is something? Well, we express that in meters. You've probably heard centimeters, kilometers, all these things. We're going to learn about what those mean in a little bit. And the symbol that we give this, and let me just make sure that this is visible. Yep, it is we give it in this little m, okay? So when you see little m, what that means is meter, okay? So very obvious and simple here. Hopefully you've seen this before, right? And the best way that you've seen meters before is if we've looked on a ruler. I'm sure all of you have. And there's these little tick marks, right? Each one is telling you how long along the meter from the start you are. So if you're here, this is 0 meters out, but let's say maybe at the end is 1 meter, a meter stick. It's a very simple idea. Okay, now let's talk about mass. Mass is a term that can be so complicated in its most fundamental physicsy form. It's basically this idea of resistance of inertia. But how we think about it on Earth is how much it weighs or how much you have. So the mass in physicsy terms is, okay, inertia, the resistance of motion, basically. But that is so unintuitive, so please don't learn it like that until you get to physics, and you have to. Mass, in our case, in the chemistry realm, is how much. Okay, so when you're in the lab and you're told get 50 grams, which is the unit of this, and is denoted G, little g. Okay, when you're asked mass out 50 grams of sodium chloride, you go out to a balance and weigh out 50 grams of sodium chloride, right? It's just telling you how much to get, basically, on your little weighing device, right? And that's all mass is. Mass is a very simple concept. Just don't learn it the very tricky way that some people like to teach it to you as. Okay, let's talk about time. Okay, in time, this is also another how long, but notice the difference in context here. Time is just telling you how long relative in time. Like you've seen time before. How long, I'm just going to write this. If I could write words today, how long, right? This is in seconds. But you can also use minutes, hours, but typically you're going to find seconds to be the most helpful. So in this case, please know that 60 seconds is a minute, 60 minutes is an hour, 24 hours is a day, just obvious stuff that you might know. 365 days in a year, I think, don't quote me on that. I'm pretty bad with that. Temperature. In chemistry, when we talk about temperature, we're basically asking, and we're going to talk about this a lot when we get to thermochemistry, but temperature is basically saying, how hot is your substance? You know what temperature is intuitively. What it's really saying, what temperature really is at the fundamental level, is how fast on average are the molecules moving. It's a scale. And that's the definition I'm going to give. How fast are the molecules moving? Molecules/atoms moving. Okay, and you're going to see two scales of this. We're going to only talk about the one a little later, which is Kelvin, which is denoted with a K. This is an absolute scale. 0 is absolute zero motion in the atoms, okay? But more intuitively, you've learned Celsius, which is degrees Celsius. You've probably also learned, I don't even know how to spell Fahrenheit, so I'm just going to give it my good old try. That is really wrong, I can already tell. So somebody correct me in the comments. But this is the basics of the metric system. That's all you really need to know for now of the base metric units. You have length, mass, time, temperature. Let's also talk about another idea here. Another idea is the derived units. So the derived units are ones that come from those base metric units. A prime example of this is area. Area is length times width if I have a box, right? Remember we just talked about length. Let's call this side L of the box. And let's call this side W, width. Okay, we know it's length times width, right? And it all it's telling you is how much space is in this area here, right? In this little box. That's all area is trying to tell you. And it's derived, it's called a derived unit because it comes from the idea of length. Length is 1D, area is 2D. Okay, so the units for this, right, when we have meters for length, well, if you do meters times meters, right, x times x, that's meters squared. Okay, so look something like that. M to the second power. Right? That's the unit we give it. Let's talk about volume. If you know what area is, I'm sure you know what volume is. If we have a little box like this, and we have some side length, and we have some width, and we have, or sorry, this should be length, right? Length, width. We also have some height of the box, right, if we're looking at it from this side. This is going to be length times width times height. This one's a very, very helpful idea, but you'll see this in some form of meters to the third power, meters cubed, but more intuitively on the metric system, we call it liters. So get used to seeing liters a lot. It's not so important to know how to convert between the two. We'll talk about it in the next video, but meters cubed and liters, This is like a standard unit on the metric system scale. This is a more of a derived unit that you can get to. But volume is a derived unit. Okay, and the last thing we need to talk about is density. So what is density? You probably heard like, oh, that cheesecake is so dense. That was weird. But why is it dense? Because there's a lot of sustenance in that piece of cheesecake, right? Hopefully you've seen, if you've had the pleasure of eating cheesecake before. But what density says is if I have like a little container, right, I have some volume. Okay, if I have some volume in space, and I want to know how many of these little red dots I have in them, okay, so let's say I have 2 in here, okay, I want to be able to express this configuration where I have 2 in this little box versus if I have like, I don't know, however many that is. Okay, how do I distinguish that difference, right? Think about how you might be able to do that. You do it with this idea of density, and density basically says take the mass, divide it by the volume that it's occupied in, and that's going to give you a density. And typically you'll see this in grams per milliliter, okay? Which is the mass, right? We talked about grams. But milliliters, we'll learn about how you might get milliliters. You also will probably just see maybe just liters, okay? Which is, again, one of our derived units, which is telling us the volume. So it relates the mass and the volume in a ratio. So if you have a density of 0.5 grams per liter versus 1.5 grams per liter, which one has more density to it? Well, you might just say, oh, the bigger number, but why? Okay, there's 3 times the amount of substance in this one than this density, okay? This density has more substance because per every 1 liter, which is in the denominator of this fraction, we have 1.5 grams versus just 0.5, right? So, and please know that how you read density, which I guess I should have explained before I said any of that, if we have 0.5 grams, it's over 1 liter, okay? So it relates the amount of grams per 1 singular liter, okay? So in 1 liter, there's 0.5 grams. In this one, it's saying for every 1.5 grams, there's just 1 liter, okay? So if the volumes here are the same, well then this density value is greater in the amount of particles it has. Okay, I really hope that I was able to drive that home for you. If not, that's okay. There are other resources other than what I can teach you here on YouTube for free. I love YouTube. This is why I'm doing this, because I think education is great. And free education, because college is expensive, guys. Very expensive. And some people don't want to pay all that money, but they want to learn chemistry, and applaud to you. Okay, I'm going to talk about prefixes now, and then we're going to do a whole lot of practice, okay? Because I think it's very, very important that you guys practice this. It is, again, a humongously fundamental piece of what you guys will be learning in this course. So let's talk about prefixes. If we have, let's say we have a nice big ruler, okay? And let's say it's exactly 1 meter in length. Okay, if it's 1 meter in length, could we divide it up into something more intuitive? Let's say I have this nice eraser here, and I put it on my meter stick. How many meters is that? Well, if you don't have any tick marks, you don't know, okay? So let's divide it up a little bit. Maybe something like, let's split it into tenths. I don't know, let's say something like that, I don't know. But let's say each tick is 1 decimeter. Okay? So then you would say that this eraser here is 1 decimeter, right? Because it goes up to the first tick line. This is the fundamental idea behind unit prefixes. what unit prefixes are trying to do is be able to teach you or show you units in a different way such that its scale makes sense. Okay, let's talk about a human body as well to really drive home this concept. If we have our nice friend Bobby here, our nice, very happy chemist friend, safety goggles here for him. And let's go into his intestines. That sounded really weird. I apologize. Don't go in his intestines. But let's say we do. Let's look at one cell. So here's his tissues. Okay, and let's just take one of these cells, okay? How long is that cell? Express it in meters. You might get something like 0.000005 meters, okay? However, we can express this a different way, because if you're in the research field and you say to someone, oh, that cell is 0.000005 meters, they're going to look at you like you're crazy, okay? It's just not something that you should be doing. Instead, refer to it as like 50 micrometers. Okay, I think that's equivalent. I didn't do the math. That's just rough. Don't take this for granted. But if instead you say, okay, it's 50 micrometers, well, it changes. You're like, okay, well, I can kind of understand that. And you'll get a grasp for these prefixes as we go. So let's talk about the scale. All right. So we have our base unit. We call this 1. So you have your volume in liters, you have your mass, right? Or you have your liters, your grams of mass, maybe your meters, how long you've moved, right? But you have different ways you can express it, and we'll learn the math behind this in a little bit with dimensional analysis. But let's say you want to go to this base unit called kilo. Well, for every one base unit, there's 1/1000th of a kilo. So in every 1 kilo, there's 1,000 of the base unit. So I'm just going to write these little facts here. 1 kilo equals 1,000 of the base unit. Okay, so you've probably seen in cars in Europe or something on your, I think it's called a tachometer, or sorry, your speedometer, okay? Maybe somebody is going 32 kilometers per hour down the road, okay? Well, notice that's in kilometers, okay? What we're doing here is, if we wanted to express that not in 32 kilometers, it would be 32,000 kilometers, right? Because if we take 32 kilos, times it by 1,000, that's 32,000. That's a lot of kilometers, okay? That's just that's unreasonable to say it that way, all right? So the way that we say this, on this scale, pay attention, very important. We're going to relate the numbers that I'm going to put up here to the base unit. So think about 1 base unit is equal to this many of this prefix. So 0.01, I think that's right. Let me just double check. No, 0.01. What I'm trying to say here is 0.001 kilo is 1 base unit. Okay, keep that in mind. That is absolutely critical that you get that. Okay, so for every 1 base unit, I have that many kilo. It's going to come in handy when we talk about unit conversions. Conversely, we could also give it an inverse relationship like we saw here. 1,000 of the base unit, 1 kilo. Okay, I'm just reversing it. I'm saying 1 base unit is equal to a fraction of a kilo, which is 0.001, or 1/1000th of it. Okay, you also have mega, which basically is another factor of 1,000 past kilo. So 1 mega equals 1,000,000. Base units, okay? So this would be 0.000001, I believe. Let me just double check. 1, 2, 3, 4, 5, 6. Yep. So that's how that would go. Let's also extend this just a little bit. There are other base units instead of, these are like the larger units, right? When you talk about like a big heaping thing of sand, you're going to want to use kilo or megagrams to express that. But what if you have really, really small quantities? How does that change? What can we express? Well, common ones you're going to see is centi. And if you have one base unit, you have 100 centi of your units. Let's also talk about milli, which if you have a millimeter, you have in one base unit of, and in this case, if you have 1,000 millimeters, you have one base unit. So 1,000 millimeters makes up one base unit. There's other ones that are really, really cool that you might be able to use if you go further into chemistry and math. You'll see this idea of micro. And I'm going to make a very important point here. When you see this thing, this is a Greek letter mu. Okay, it comes from the Greek alphabet. You're going to start to see these a lot. When you see this little mu, that's micro. And basically what that's saying is one million. So if you have one base unit, you have 1 million micro base units of that. We can actually take this even further. If we talk about nano, which is denoted with a little n, right? That's 1 billionth. Or if you have one base unit, you have 1 billion nano of whatever you're talking about. So notice how we're really exploding in magnitude here. Let's also understand what the prefixes we add here. So for milli, we're going to add a little m. For centi, we're going to add a c. I should have known that. Base unit's just the base unit, and then kilo is a k. Mega is, unlike milli, it's a big M. Okay? So relative to a base unit in its magnitude, I'm going to review this one more time because I really want it to go home. If I have, let's say, for example, one base unit, I have 1,000 milli of those units. So let's say I have 1 gram of something in my hand. I have 1,000 milligrams of it. Or I have 1 million micrograms of it. Or I have 1 billion nanograms of that. Okay? If I have 1 gram of something, I have 0.001 gram of it. Here are the notations that we put. And for example, just to show you where these come into play, the little prefixes, if we have 1 gram, that would be equal to 1,000 milligrams. See the difference in notation here, right? We just add a little something to denote what it is. And we're going to learn the math behind this, but it's fundamental that we understand the scale first, and then we'll be able to evolve that into using it in a more mathy sense, in a more, useful way. Okay, keep this in mind, keep this in your notes. We're going to talk about that later, but what we're going to do now is just do a couple simple practice problems, and we will go from there. Okay, let's play a game here. Let's first identify what units that we're talking about in this hypothetical. Let's say we have a box, and inside of this box, let's put 3 cats. Oh, this marker's dying, guys. I'm sorry, no red cats, apparently. Let's see if we can have purple cats. Maybe life will be great now. Oh yeah, look at that. We're going to have purple cats in here. Okay, so we have 3 cats in this box, okay? And let's say that it has some length. This side length is 0.02 meters, okay? Let's say that this length is 0.04 meters, and let's say that this length is also 0.02 meters. Okay, so notice these are all lengths, okay? So I'm giving you that. And let's say each, cat here is 2 grams. Yeah, that's not a cat, that's probably more like a kitten, but bear with me here. So we have 2 grams per cat, and we have 3 of them. So overall, here's what I want you to find. Total mass in grams. So what's the total amount of substance in here, like the sustenance of it? Okay, how many grams of it do we have? Secondly, I want you to find the area of this bottom plate here. So find area of top or bottom of box. So just to be clear, when I talk about that, right, if here's the box, I'd like you to find this area up here or this area down here. So the top or the bottom of the box. Okay, another thing I want you to do is find the area, or sorry, find the volume of the box. And then fourth, find the density. And for all these, give units, give some sort of explanation. And you can go ahead and pause the video then. Okay, so hopefully you've tried this. Let's talk about finding the total mass. So notice that there's 3 cats in total, right? 1, 2, 3. If there are 2 grams in mass, sorry, I just want to make sure that we can, I'll put my work down in here, I suppose. So for 1, there's 2 grams per cat, and we have 3 of them. 2 times 3 is 6, so there's 6 grams in total. Smiley face if you got that, frowny face if you didn't. Just kidding, only smiley faces, only positivity here. Well, what about the area of the top or bottom? Well, we need to do length times width. Okay, so notice we have, we need to know that either the top or the bottom, and we know those lengths, the length and the width, that's 0.02 meters and 0.04 meters. And if you take your calculator and simply type that in, something like that, okay, you're going to find the area to be 0.0008. But what's the unit? Is it meters still? Well, no, it's meters squared, right? Because we've multiplied a meter times a meter, that's meters squared, okay? And I'll just denote that that is indeed area. Okay, let's now also talk about the volume. So it's just like we did last time, but it's length times width times height. So just like last time, 0.02 times 0.04 times 0.02, something like that, okay? When you do that, you're going to find it to be 0.000016 meters to the 3rd power, and that's the volume of the box. So even though this number looks small, remember that it's representing a 3D space, right? So small volumes can still be quite large, even though the side lengths might not, or the small value magnitude might make you think otherwise. Okay, now for the hard part, let's calculate the density, right? If we remember what density is, remember that's mass over volume. So we have 6 grams in total. And what volume is that occupied? And well, we know the volume here is 0.000016 meters to the 3rd power. Okay, such that density, if we take the fraction of the two, which would look something like that, the density is going to be, oh, this is a pretty extreme density. I should have picked something a little better. when we calculate the density, it's 375,000 grams per meter cubed. So a really large density. So that's all you need to know really for this section. Let's talk about one more thing before we end this lecture. We're going to talk about scientific notation. That's important, and I forgot to mention that we should have talked about that. But it is very important that we understand scientific notation. So prefixes work in scaling, right? We talked about this. And we're going to learn the math behind it and how to calculate. If we have a very, very small mass, let's say something like this little speck here, right? Hopefully you can see it, that little eraser chunk. How can we represent that mass? We could say it's 0.0000001 gram. We could also refer to it as like 1 microgram or something small, okay? But there's another way to do it, and that's with scientific notation. Scientific notation takes really small or really large numbers and make them in a compact form. How do we do it? Let's take that example of the eraser chunk. Let's say that it was 0.000003 grams. What in the world do we do now? Well, there's a really easy way to represent this, and I'll show you how to do it. You've probably seen this before. This little weird times 10 to the negative blah, 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 or positive blah, blah, blah. What this is telling you, and if you need more help on this, please watch another video. I'm only going to really go over it very shortly, but this is telling you how much to shift the decimal point. When you see times 10 to the negative 7, it means starting from here, move your decimal point 1, 2, 3, 4, 5, 6, 7 spots. Put your decimal there, and that's your number. So it basically takes this long strand and condenses it down into something really small. Let's do another example of a smaller number just so you can kind of get the groove of it. Let's say we have 0.000025 grams. Okay, how might we express this? Kind of like this one where we only have one number here. Well, what we're going to do is, we notice that this is a small number, so the exponent in this case will be negative. And I'll write a note about that. Negative equals small, positive exponent means large. And we'll get to a large example in a second. If I have this, I can shift the decimal point 1, 2, 3, 4, 5 spaces, call this 2.5, right? I'm shifting the decimal place this way, and it's times 10, 1, 2, 3, 4, 5, that's negative 5, okay? So this is just kind of like a shifting factor, so to speak, and it's really unintuitive to get your first couple go-arounds, but once you do it enough, once you work with scientific notation to a high degree, you'll be fine. And honestly, Organic Chemistry Tutor has great videos on this if you need more on this. Let's do 3 more examples. Let's do a larger one. 250,000. What's that in scientific notation? Well, here would be where your decimal is, right? Because that goes into the decimal places. If we move it 1, 2, 3, 4, 5, put it here, call it 2.5, we can move, and again, let's move 1, 2, 3, 4, 5, right? This could be 2.5 times 10 to the 5, positive 5 grams. What about a million? How can I express a million in scientific notation? Well, here's your decimal place. Go 1, 2, 3, 4, 5, 6. You're going to call this 1.0 times 10 to the 6 grams. So don't be alarmed when you see this times 10 to the blah, blah, blah power. It's just telling you how much shifted you are from where the decimal place actually is to this number here, which in this case is 1.0. So we're saying literally 1.0 times 10 to the 6. And if you want a more in-depth idea, this is 1, the value 1 multiplied by 1,000,000. Because 10 to the 6, right, multiply 10 by itself 6 times, you get 1,000,000, right? When you do that math, you get 1,000,000. So just in case you want a little more depth. Okay, let's do one more example. Let's do 0.075, okay? Express that in scientific notation. Actually, I want to do another one after this, but go ahead and do that while I write this one out. Okay, so 0.075, we could express this as, if we move the decimal place over, that's going to be 7.5 times 10 to the negative 2. Okay? Okay, now let's talk about this one. This one's reversed. So instead of making you go from a very long, crazy number to scientific notation, go from scientific notation to big, crazy numbers. So basically, reverse psychology. Okay, so let's go ahead, notice this is -5, so we have a small number, and when we have that, what we're going to do is shift the decimal place 5 units that way, right, you can think, from the 3.75, make the number smaller. So the way that I like to do this is start here, 1, 2, 3, 4, 5, put your decimal place in between those zeros, and then rewrite your number 0.000375, and in this case I specified it was grams. So notice we made it dumber by referring to this really crazy big number. Okay, that's all I had to do about measurements today. Hopefully you found it helpful. If you did, please drop a like, comment, subscribe. Next time we're going to get into dimensional analysis. We're going to do tons of practice problems. We're going to work with all this math again. I'm going to throw do scientific notation here, do length, do mass, do volume, do area, do density, all this stuff to make you get really comfortable with it. Alrighty guys, thank you. Take care.